Okay, so I can hear you, but let me introduce the first speaker and let him speak. And so the first talk is on a screen, and it's a joint work with Anatoly Serdyuk and Igor Sokolenko. Igor, please go ahead and start your talk.
Thank you, Alex. First of all, I thank the organizers for the opportunity to make a talk at the International Scientific Online Conference, Algebraic and Geometric Method of Analysis, dedicated to 160th University of Dmitry Alexandrovich Grave, academician of the Ukrainian Academy of Sciences, the first director of the Institute of Mathematics of Ukraine. The title of the talk is Asymptotic Behavior or the width of classes of the generalized Poisson integral. It is a joint work with Professor Anatoly Serdyuk. Let LP, L infinity and C be the space of two periodic functions with standard norm LP, L infinity and C, and let B0P be a unit ball of the space LP of function phi, which orthogonal to 1. Denoted by C psi O and beta P, P lies between 1 and infinity included, the set of all two periodic functions F, representable as the convolutions of form 1, with the fixed generated kernel psi O and beta, the Fourier series of which has the form 2. Here, beta O and beta is a sequence of even but psi of k greater than or equal 0. A function f in the representation 1 is called the psi O and beta integral of the function phi, and is denoted by e psi O and beta phi. If psi of k don't equal to 0, then the function phi in representation 1 is called psi O and beta derivative of the function f. The concept of psi O and beta integral and psi O and beta derivative was introduced by Stepanet. The case beta k is intrinsically equal real beta. The classes C psi O and beta p are denoted by C psi beta p. All psi of k is equal to k in power minus r are greater than 0. The classes C psi O and beta p and C psi beta p are denoted by WR O and beta p and WR beta p respectively. The classes WR beta p are well-known Weyl-Knight classes. In other words, WR beta p, p lies between 1 and infinity included, are the classes of the periodic function f, representable as convolutions of form 2, of form 3. The Weyl-Knight kernels BR beta for the form 4. With the function phi belongs to unit ball B0P. The function phi in the formula 3 is called the Weyl-Knight derivative of the function f and is denoted by fr beta. If r is a positive integer and beta is equal to r, then the function br beta of the form 4 are the well-known Bernoulli kernels, and the corresponding classes WR beta p coincide with the well-known classes WRP, which consist of two periodic functions f with absolutely continuous derivative fk up to r minus 1's order inclusive, and such that LP norm f r derivative not greater than 1. In addition, for almost everywhere x, fr derivative of x is equal to phi of x. Phi is the function from 3. For psi of k is equal to e in power minus alpha k in power r, alpha and r greater than 0, the classes c psi over and beta p and c psi beta p are denoted by c alpha r over and beta p and c alpha r beta p respectively. The sets c alpha r beta p are well-known classes of generalized Poisson integral. Set is classes of convolutions of form 5 with generalized Poisson kernels of form 6. Let calligraphic n be a some-functional class from the space C. The quantity of form 7 is called the best uniform approximations of the class calligraphic n by elements of subspace tau to n minus 1 of trigonometric polynomials n minus 1 of order n minus 1. The order estimates of the best approximations ENKC of classes C psi over and beta p and hence classes WR beta p, C alpha R beta p and C psi beta p, depending on rate of decrease into 0 of sequences psi of k, obtained in particular in works of Temlyakov, Rabova and Serdyuk and Stepanik. If the sequences psi of k decrease to 0 faster than any geometric progression, then asymptotic equation of the best uniform approximation are even known. So, see, for example, the author's work 23 and the bibliography available there. In 23, it was shown that for such classes C psi O and beta p, the following asymptotic equations take places. The value of best uniform approximation is asymptotically equal. The value of deviation of Fourier sums of these classes. The value of deviation of Fourier sums classes C psi O and beta p has the form 9. Here is Sn minus 1 of f is a partial Fourier sums of order n minus 1 of the function f. For p equal infinity, in the case k is equal to r over n beta infinity r greater than 0, and in the case c alpha r over n beta infinity r greater than or equal 1, and in the case c psi over n beta infinity, for certain restrictions on sequence psi and over n beta, the exact value of the best uniform approximations are known thanks to the work of Favar, Ahiezer and Crane, Nagy, Stechkin, Dziadek, Sun, Ushansky, Pinkus, Serdyuk, and others. For p is equal to and arbitrary overline beta, under this condition, the exact values for the quantity of calligraphic En C psi O n beta 2c are also known. We established two-side estimates of the Kolmogorov-Bernstein linear and projection width of the classes C psi over n beta 2 in the space C, which become into asymptotic equation variation under certain restrictions on the sequence psi, in particular if this limit is equal to 0. Definitions. Let K be a convex centrally symmetric subset of C, and let be a unit ball of the space C. The quantities Bn Kc of form 10, Dn Kc of form 11, lambda n Kc of form 12, and Pn Kc of form 13 are called the Bernstein, Kolmogorov, linear and projection and width of the set K in the space C respectively. The results containing order estimates of width 10, 13 in the case of K is equal to C psi O and beta P, and in particular WR beta P and C psi beta P can be found, for example, in the monograph of Tikhomirov, Pincus, Kornichuk, Romaniuk, Temlyakov, and others. The main statement is the following theorem. We let overline beta is a sequence of real number and psi of k greater than 0 and satisfies the condition 14. Then for all positive n and for any width bn, dn, lambda n or pn, the following inequalities hold 15. If in addition psi of k satisfies the condition 16, then the following asymptotic equalities hold 17. Here O of 1 are the quantities uniformly bounded in all parameters, and the equalities 17 are realized by trigonometric Fourier sums as n minus 1 of f. We give the corollaries of theorem 1 in the some important special cases. Note then the condition 16, this condition, this limit is equal to 0, is satisfied if psi of k satisfies the D'Alembert condition D0 of form 18. Corollary 1. Let overline beta be a sequence of real number, and the sequence psi of k is strictly decreasing and satisfies the condition D'Alembert D0 of the form 18. Then, as n tends to infinity, the asymptotic equalities 17 holds. This asymptotic equality holds. Theorem 2 for the clusters Weymad, WR, O and beta. Let O and beta be a sequence of real numbers and positive integer. Then for all r greater than or equal n plus 1 divided 2, the following inequalities hold. Maintain. Here P and P2n is any of the widths Bn, Dn, lambda n or Pn. And note that if the condition, these limits r divided n is equal to infinity, is satisfied, then for c of k is equal k in power minus r, the condition 18, this condition, this limit is equal to 0, is also satisfied, and we have theorem 3. Let r greater than 1, m is a positive integer, O and beta is same as in theorem 2, and the condition 20, this condition is satisfied. Then the following asymptotic equalities hold. Equalities 21. Here, all of 1 are the quantities uniformly bounded in all parameters. Theorem 4, that when beta is a sequence of real number, alpha greater than 0, r greater than 1, n is a positive integer, and all b such that this condition 22, then the following inequalities hold. 23. In these inequalities, Pn is any of the widths Bn, Gn, lambda n, or Bn. And the next theorem, theorem 5, let O be the same as the theorem 4. Alpha greater than 0, r greater than 1, n is a positive integer, and the condition 22 is satisfied. Then as n tends to infinity, the following asymptotic equality called 25. In this equality, Pn is any of the widths Bn, Gn, lambda n, or Bn. Gamma alpha n is defined by 24, and O of 1 as a quantity uniformly bounded in all parameters. Note that theorem 5 complements the results of works of Sheloudin, Stepanets, and Serdyuk, Arthur, Serdyuk, and Bodenchuk, which contain exact estimates for the width of the classes of convolution with classical or generalized Poisson kernels. The asymptotic equalities 25 are realized by trigonometric Fourier sums. The asymptotic equalities for deviation of Fourier sums on classes of generalized Poisson integral C alpha A beta P in the uniform metric are seen, for example, in the work of Stepanets, Serdyuk, and Stepanets and others. This work was particularly supported by the grant Sompati spectral optimization for mathematics to physics and advanced technology. Reference here the Crane, Shansky, Yadek, Drabova, Serdyuk, Pawar, Kornichuk, Bobenko, Legun, Crane, Nagy, Pinkus, Romanyuk, Serdyuk, Bodenchuk, Serdyuk, Stepanyuk, Sheloudin, Stechkin, Stepanets, Sun, Temlikov, and Tikhonov. Thank you for your attention.
Thank you very much. Let's thank our speaker. So feel free to unmute and to clap. I hope you can hear me now. I can hear you. That's great. We have a couple minutes for questions. Do you have questions? Please feel free to unmute and ask. Any questions so far? I have a quick question. You prove that equivalence of some for this asymptotics for all these quantities B, D, lambda in that particular case, but say, and you gave a quantitative estimate, right? But say, would it be easy just to prove that all of them have the same asymptotics, just without specifying what kind of asymptotics, or it's kind of too crazy question?
This kind of asymptotic is the best uniform approximation, yes? Is asymptotic liquid to value of deviation of yes and yes or other asymptotic. I don't care.
So in your theorem 5, you say that afterwards we have for all fours we have this asymptotics holds for all b, d, lambda, and pi n. So my question, could it be easy to prove that they have the same asymptotics just without going to specification what asymptotics?
This asymptotic has the main term, 1 divided square of p, and second term O of 1. This is the value is bounded, uniformly bounded in all parameters alpha, a, beta, and gamma alpha Rn is defined by this formula. Here, if we have the condition 10 to 2, this is equal to 1. If n tends to infinity, this is small, tends to 0, and we have gamma alpha n tends to 1. So we have 1 divided root of p plus O1 and e in power minus alpha r n minus 1 r minus 1 tends to 0.
Okay, so let's sense our speaker again. Thank you very much.